So let's start doing some calculus with these parametric functions. So we're going to work with this parametric function right here. X of t is 2 plus cosine t, y of t is negative 1 plus sine t, and our t values go from 0 to 2 pi. And I've gone ahead and used GeoGebra to plot the graph for you. It's a circle that's been shifted, and just to show you how the graph was plotted with t values going from 0 to pi to 2 pi, I have labeled a point P that's going to travel around the circle as the points were plotted. So when t is 0, P is at 3, negative 1. And in this case, the graph was plotted counterclockwise. So as t ranges from 0 to 6.28 or so, you can see how our graph was plotted. All right, so we'll refer back to this graph several times during this presentation to verify the results that we're getting on paper. Okay, so first of all, derivatives that we can calculate with this data here, this parametric curve, and what do they tell us? So I have x equals 2 plus cosine t. The derivative I would calculate there would be dx dt. Okay, x is the dependent variable. In this case, t is the independent variable. So dx dt, or if you like, you could say x primed of t, same thing. We like both notations in different contexts. One I can keep the input steady, and the other one I can use as symbolic. What do we get? We get negative sine of t, and y primed of t would be same as dy dt symbolically, and that's going to be equal to cosine t. Okay, simple enough. Now, what do these tell us? Okay, well, we've been used to dy dx and derivatives of that nature, but just remember the pattern. This is the rate of change of this variable with respect to this variable. So dx dt is the rate of change of x with respect to t, and the dy dt would be the same thing except we're talking about y. When we talked about normal derivatives, when the derivative was positive, it told us that our quantity was increasing. Okay? And when the derivative was negative, that told us our quantity was decreasing. So if dx dt was positive, what would that mean in terms of our graph? Okay, well, it's going to mean that the x is going to increase. In other words, the x-coordinate will be getting larger. Okay, so let's see here. X is increasing, and what does that mean? I guess that means that as far as right and left goes, your curve is being traced off to the right. Hope that makes sense. That if I was drawing the curve and my dx dt was positive on an interval, that means I would be moving from left to right rather than from right to left. And vice versa, if dx dt was less than 0, then my x-coordinates would be decreasing. These tell you when your x or y coordinates are increasing versus decreasing. I wrote those out there in red down below. Let's take a look at one specific value, and let's see if it makes sense with our graphed curve, what we see here. So let's just do pi, for example, okay? Or not pi, let's use pi over 3. So x primed of pi over 3, okay, would be the negative sine of pi over 3, which is going to be negative square root of 3 over 2. So we get a negative value here, okay? So that's going to mean that my x value will be on an interval that x is getting smaller when I look at the graph, and we'll take a look at that in a second. And y primed of pi over 3 was going to be down here the cosine of pi over 3, which is 1/2, which is positive. Okay, so if we go to the graph and we type in t equals pi over 3, it should put us at a place where my x-coordinate was getting smaller and my y-coordinate was getting larger. And if you remember how our graph was being plotted, it's being plotted counterclockwise. That is the case. The x-coordinates are getting smaller on this interval that pi over 3 is a part of, and the y-coordinates are getting larger because I'm moving left and upward on the curve. So that jives, that meshes. Okay, now let's take the derivative a little step further, and let's talk about the critical points. Okay, what happens if dx dt equals 0, and what happens if dy dt equals 0? Well, in the past, this has meant no rate of change for your quantity. So in this case, no rate of change for x, right? 0 rate of change. So your x-coordinate is not changing. The x-coordinate is at rest, so to speak. Okay. Now we know that that means I could be changing direction, and we also know it could mean I'm just at rest for that moment and going to continue on. Okay, and the same thing here, the y-coordinate would be unchanged. Now, if you get a sign change, okay, then that will tell you either a maximum or minimum x-coordinate, maximum or minimum y-coordinate. All right, let's take a look at the example here and see what we get for critical points and what that would tell us. And remember, we are restricted to this interval 0 to 2 pi for this particular example here. Okay, so the derivative of x with respect to t, once again, was negative sine of t. And if we make a sign chart for the derivative dx dt, when is sine of t equal to 0? That happens at pi. Also happens at 0 and 2 pi, but those are endpoints. All right, prior to pi, the sine function is positive with this negative, makes everything a negative. And after pi, sine is negative, but the negative sign in front makes that a positive. So this tells me that when t equals pi, x is at a minimum, local minimum. I would compare with 0 and 2 pi to see if it was an absolute minimum or not. And what would that minimum point be? Well, let's see here. X of pi comes out to be 2 plus the cosine of pi, which is negative 1, so 2 plus negative 1 is 1. So let's take a look and see if that's the case or not. If I type in t equals pi, look where it puts point P. Okay, it puts point P at the farthest left that circle gets. That's the minimum x value on this curve, and it is indeed 1. Okay, so far that's nice. It's matching what I expect. Okay, let's take a look at the y derivative and what that will tell us. Once again, was cosine of t, and if we make a sign chart for dy dt, cosine is is 0 at pi over 2 and 3 pi over 2. And this is just unit circle knowledge right here. Cosine is positive, then it's negative, then it's positive. So when t is pi over 2, okay, I should see a maximum y value, local maximum, and that value would be the sine of pi over 2, which is 1 minus 1, so 0, max y of 0. And when t is 3 pi over 2, I should see a min y of negative 2. Okay, so let's take a look. So pi over 2 and 3 pi over 2 are my points there. T equals pi over 2 puts me here, maximum y value of 0. And t equals 3 pi over 2, minimum y value of negative 2. So very good. We are seeing on the graph what the paper says we should see here. Next, let's take a look at how do you find the slope of a parametric curve. Okay, and we want to remember that slope in the xy plane is given by this expression right here, dy dx. Okay, that would be the derivative of y with respect to x if we had a function y equals something in terms of x. And we could try to do that by limiting the parameter, but that's not always possible in the parametric world. So somehow we need to come up with dy dx from the two derivatives that we know that we can calculate, which are dx dt and dy dt. Okay, and if you are willing to treat these as fractions, then you can clearly see that if I do this calculation here, okay, I would get dy dt times dt dx. And if I treated these as fractions, I could cancel the differentials, and I would get dy dx, which is what I'm looking for. Okay, so this expression right here is how you will find the slope of a parametric curve. You'll take the derivative of y with respect to t and divide it by the derivative of x with respect to d. And this will still be a function of t, but it will give you the slope of the curve. So dy dx will come out to be negative, let's see, cosine over sine is cotangent, correct? Okay, so you could write it like that, or if you want, you could write it as cosine t over sine t. Now what's this good for? This is good for finding the slope of the curve, which means it's good for finding where there are horizontal tangents or where there are vertical tangents. So for example, whenever cosine of t is 0, you'll see a horizontal tangent on the graph, and whenever sine t is 0, you'll see a vertical tangent on the graph. And we've already seen spots where that occurs. Okay, so you could find where this happens, this horizontal tangent, or this horizontal tangent, or these two vertical tangents, by analyzing the derivative dy dx. You can also write equations of tangent lines, because this now can give you the slope of the curve for any time t. The second derivative, kind of interesting, because this is the concavity finder, right, for the curve, and it has a symbol that looks like this, right? D squared y dx squared. And so we have to come up with this calculation based on the things that we can do, okay? Now, we know how to calculate dy dx. That was the last slide. We can take, and remember, let's go back and take a look. Dy dx was a function of t, so it's not a function of x. So it's not as simple as, okay, just take the derivative of this with respect to x. Well, you can't because it's a function of t. So what you can do here is take the derivative of that with respect to t, okay? That you can do. Now, what would that give us? Okay, that would give us d squared y, which is what we want in the top, but now in the denominator you have dt dx, dt times dx, which is not what we want. We want dx times dx, right, dx squared. Okay, so there's a calculation we can do to get us d squared y dx squared. Okay, you want to cancel this dt and you want to get another dx in the bottom, so you would get that by multiplying this by dt over dx, or written another way, okay, you would do d squared y, okay, over dt dx, that's what you had, all right, divided by dx dt, which you can calculate, okay. That will give you the calculation you're looking for. Okay, so I know I've got a whole bunch of jazz here that is kind of ugly to look at. So let me just recap what you would do to find the second derivative. Okay, you're going to take the derivative with respect to t of the first derivative, and then you're going to divide by dx dt. Now, if you forget all that, you just got to kind of play with the calculations to see what you're after. Okay, this is what you're after: d squared y dx squared. Okay, so let's try it with this example. We saw on the last slide here that dy dx could be written as negative cotangent t. Okay, so what do I need to do to calculate the second derivative? I need to take the derivative of that with respect to t, so d dt of negative cotan t divided by dx dt. Right? And what was dx dt? It was negative sine t. Okay. What is the derivative of negative cotangent t? Let me think here. It's negative, well, the derivative of cotangent t is negative cosecant squared t. So the negatives cancel, and I'm going to get cosecant squared t, and divide that by a negative sine t, which is fine. It won't be the multiple choice answer, because this is going to be really what? This is another cosecant that can be written at the top, so you could say negative cosecant cubed t. Okay, so this is the concavity finder for your curve. You can analyze the t values for which your curve is concave up or down based on the second derivative. Okay, but this is your formula that's going to get you that. If you forget it, just play around with the symbols until you get to d squared y dx squared. Last little concept we're going to look at here is the length of a parametric curve. And let's just go back and remind ourselves, when you zoom in on a curve, it will look like a line as long as your curve is differentiable. So we'll say that this is our curve, x of t, comma, y of t. And if I draw some line segments here, I can make a right triangle. So we're assuming that this is a point in the xy plane, so is this. Okay, and this distance here is a change in x. Okay, and this distance here is a change in y. And our changes in x and our changes in y are with respect to t here. So this is dx dt, and this is dy dt. And again, notice that if you take dy dt divided by dx dt, you would get the slope of this curve, dy dx, which is what we expect. Okay, well, your curve looks like a line when you zoom in. This is a right triangle. I can find the distance between these 2 points with the Pythagorean theorem. Okay, so the length of the curve, at least when I zoom in, is going to be the square root of dx dt squared plus dy dt squared. Okay, and if you're saying this looks familiar to the formula, how we derived the other length of the curve formula, you're right. Okay, this is how it started it off. It started off the same way. Dy dt squared. Okay. All right, now that works on a very small interval when your curve looks like a line, and you would go to the right and get the next interval and do the same thing and go to the next interval, and then you'd add all those up. How small do you want your intervals to be perfect? You want your interval to be very small. So the way to do this is to shrink all these intervals down to almost nothing and add them up, and that's done with an integral. So the length of a parametric curve is going to be found with the integral from t1, okay, time 1, not necessarily time 1, but t value 1 to t value 2 of the square root of dx dt squared plus dy dt squared. Then dt is your differential. Graph, it's a circle of radius 1, so we know the answer is supposed to be 2 pi r, and if r is 1, then the length of this curve should be 2 pi. So let's see if the calculation actually marries up with that. Okay, we have already done the calculations for dx dt and dy dt a couple of times here. Alright, 0 to 2 pi are the t values for this particular curve, and we have the square root of dx dt squared, which will give us sine squared t, plus dy dt squared, which will be cosine squared t. And you're saying, aha, that's very nice, because sine squared t plus cosine squared t is going to be 1. The square root of 1 is 1. And so I'm integrating 1 with respect to t. So I get t evaluated 0 and 2 pi. And so we do get 2 pi is the length of the curve, which matches what I expect. Okay, so try 10.2 number 37.